So the topic of my presentation is shoulder kinematics. And before I start, I would like to ask a question. Why does it matter to look at shoulder kinematics? Shoulder injuries are one of the most common type of injury in human body. And in the case of a full thickness tear of a cuff muscle, the current best solution is total reverse shoulder arthroplasty, which has its own limitations. So understanding the shoulder kinematics could have high clinical importance. Let's start by introducing the human movement system. The human movement system includes an integration of the nervous, skeletal, and muscular systems. The nervous system. The nervous system is composed of two interdependent divisions, the central nervous system and the peripheral nervous system. The central nervous system includes spinal cord and brain, and peripheral nervous system connects the rest of the body to the central nervous system. And for the purpose of shoulder kinematic, I think a subdivision of peripheral nervous system, which is somatic nervous system, is of high importance to understand the shoulder kinematics. Next is the skeletal system. And since we are looking at the shoulder kinematics, I will only introduce the bones of upper extremity, which are scapula, humerus, clavicle, ulna, and radius. It is also worth mentioning the different types of synovial joints, which, for the purpose of my study, which was on shoulder kinematics, the important synovial joints, I think the glenohumeral joint is a shallow ball and socket synovial joint, and the type of joint of acromioclavicular and sternoclavicular joints are, and their arthrokinematics are not defined by the Society of International Biomechanics or something. Next is the muscular system. The muscular system links the nervous and skeletal systems and is responsible for generating the forces that move the human body. Now, let's introduce the muscles of upper extremities. The most important muscles, and I guess most common type of injury that happens, are for cuff muscles. And cuff muscles are comprised of supraspinatus, subscapularis, infraspinatus, and teres minor. And another group of muscles, important muscles for mostly doing the abduction range, abduction movement of the arm, are the deltoid muscles. Also, I think it's two important muscles are pectoralis major and pec minor, which are, I think, their role is not very well understood in any shoulder upper extremity movement. Now let's introduce the different types of muscle actions. First is isotonic. In isotonic muscle action, the force is produced, muscle tension is developed, and movement occurs at the given range of motion. Next is isometric muscle action. In isometric muscle action, the muscle tension is created without a change in muscle length and no visible movement of the joint. And last is isokinetic. And in this type of muscle action, the speed of movement is fixed and resistance varies with the force exerted. Next is the functional anatomy of muscles. Muscles can be divided into four categories: agonists, synergists, stabilizer, and ontogenists. The agonist muscles are the prime movers of any movement that occurs, and synergists are kind of supportive and supports the agonist muscles. And stabilizers, which is, I think it's obvious from their name, do the stabilizing action of joints and bones, I suppose, and the antagonists are the opposite of agonists muscles. And it could vary depending on different movement. For example, some of the, I believe, some of the stabilizers of the glenohumeral joints, like the cuff muscles, in some movement will do the function of agonists. For example, like internal rotation to the back, and depends on whether you standing up or lying down, it will be different and it will affect. So I want to narrow things down to the focus of my research. The shoulder complex is comprised of four distinct joints: glenohumeral, acromioclavicular, sternoclavicular, and scapulothoracic. Understanding each of these joints' function and amount of contribution during any upper extremity movement would have significant clinical importance for different injury treatments. Now, let me introduce acromioclavicular joints and its surrounding ligaments. As I mentioned before, the arthrokinematics of this joint is not defined. And also, what I mean by arthrokinematics is the movement happening in the joint, while the movement of the bones is commonly known as osteokinematics. So the important ligaments are trapezoid ligament, conoid ligament, coracoacromial ligament, and the acromioclavicular capsule surrounding the joint. And this joint is where the distal end of clavicle meets the acromion side of scapula. The question that I tried to answer for the past couple of months with my research was that, is there movement in this joint? And the method I used was 4D CT imagery. And it was in a way that 4D CT images of 7 old participants with a possible degenerative AC joint were selected. 3D bone segmentation of CT images was done for the first half of the motion, internal rotation to the back, using 3D slicer software. Then low resolution dynamic models were registered on high resolution static ones. Finally, the interbone distance was calculated using an algorithm. And I added the result of 3 patients, as you can see, with different frames of motion. the interbone distances would vary in this joint. And I found a study on a long-term follow-up of rheumatoid with people with rheumatoid AC joint, and the space of the joint was 8 millimeter. So that was the threshold I used for my study. And as you can see, in the areas that are more red, it means that the two bones are closer to each other. And by looking at the color maps, I think there is absolutely movement in this joint. But unfortunately, I was not able to detect any specific pattern because of the low sample size of my research. So after seeing all this and reading, reviewing the literature, an idea came to my mind, and it was the possibility of proper scapula classification. But before we can do that, I think there are 3 questions that must be answered. First is that, is there a relation between rotator cuff tear and scapular morphology? Second is that, does morphology drive function? And the last question would be, what could be achieved by looking at the evolutionary study of bone morphology? And then I want to review what has been done so far in the literature. But before, I would like to introduce Wolff's law of trajectorial orientation, which proposes that trabecular struts align with the orientation of dominant compressive loads within a joint. Actually, Poncer in 2006 did the experiment on juvenile guinea fowls, and what he managed to prove was that the orientation of maximum density, trabecular density, will change to match the orientation of maximum loading. A few years later, Colin Shaw and Jay Stock did a study on human athletes on the diaphyseal rigidity and shape of humerus, and also investigated the effects of compressive loads that produce high mechanical strengths. So it's an important concept. And in 1986, Bagliani proposed an acromion classification based on supraspinatus outlet, and he decided that we have 3 types of acromion, which type 1 is flat, type 2 is curved, and type 3 is hooked. There's been another study in India, in the Department of Anthropology, of course, trying to classify acromion, and they were suggesting the similar patterns of acromion shape. Also, in another study, it was shown that the end stage ball and socket AC joint, end stage degenerative AC joint, and as you can see, the osteophytes in the acromion side. I think that it will act like a ball and socket, but it's not always the case. Like I said, the arthrokinematics is not fully defined yet. And also I found a study on right clavicle of different primates and their evolution, as you can see. And in humans, it's very, in modern humans, the clavicle is very, very, what do you say, curvy. And this is also important because this is the other side of the AC joint. That's because what is a joint? It's an intersection of the end of two bones. Also, this was another cool study of scapula shape and evolutionary study, and this was the scapulas that I created with the CT images from the CT images of our patients, and I also found a study on which was very interesting. They were looking at stress distribution of two different loading scenario on primates, which were either bipedal and quadruped, arboreal or terrestrial primates. And what they found was that the distribution of maximum loads, the distribution of stress in that two different scenario was actually different. And think about Wolff's law and Poncer findings and this kind of analysis in a finite element analysis on a scapula. It was sounded very interesting idea to investigate the effect of mechanical loads, cyclic loads on the morphology and shape of this bone. So at the end, I would like to introduce my hypotheses, which is current imaging modalities have enabled us to assign material properties for subject-specific studies. Obtaining Young's modulus of bone with the help of radio density in CT images and comparing the concentrating area of maximum stresses in shoulders with different geometries could be useful for the classification of shoulder blades. I believe, a proper classification of shoulder blade could be achieved based on the shapes of coracoid process, acromion, and glenoid cavity. And I believe that morphology drives function. That was the end of my presentation. Thank you all.